Okay, so far we've looked at probability, we've looked at how that affects expected value, and then we've also looked at keywords like or, not, and odds. So now we're going to look at the keyword of and. Okay, so two events are independent events if the occurrence of either of them has no effect on the probability of the other. For example, tossing a coin 2 different times. When you toss the coin the first time, that is not going to affect what happens when you toss the coin the second time. So they're completely independent events. Now, this is different than mutually exclusive. Okay, I want to make sure you guys don't get confused with those two terms. Independent events means that you're actually doing two completely different activities. Whereas mutually exclusive means you have one activity happening, drawing one card, and can that card be two different things at the same time? Okay, so it's mutually exclusive means one event is occurring, and can that event have two different characteristics at the same time? Whereas independent events means you have two completely different events going on, and they don't affect each other. All right, so a die is rolled, and then a coin is tossed. Find the probability of rolling a number greater than 3, and then the coin landing on heads. So these are independent events, because when you roll the die, that's not going to affect what happens when you toss the coin. Okay? Now, there's two ways we can do this. What you have done in the past is you've looked at what all the outcomes were. And a lot of the times the book did this for you, is they listed your sample space. For example, you could roll the die and get a 1, and flip the coin and get heads. Or you can roll the die and get a 1, and flip the coin and get tails. Right? Those two different things that you can get. So here are all the different events that could happen. So after you've listed this sample space, then you can find the probability of rolling a number greater than 3, and then the coin landing on heads. So in this list of 12 items, how many times does that happen? Okay, 3 times, I heard. So we've got, okay, so we've got the 4 in heads, 5 in heads, and 6 in heads. So that would be 3 out of a total of 12. And so the probability of greater than 3 and heads is 3 out of 12, which reduces to 1/4. Now, I gave you this list. I could have said, I'm not going to give you the list, and you'd have to generate that list on your own. Okay, a little tedious to come up with that, not super hard, but you have to know what you're looking for. The other way you can do this, if you have a keyword of and, is that you're going to take the probability of the first event and multiply it times the probability of the second event. Okay, so when you see a keyword and, that means you're multiplying probabilities, as opposed to the keyword or, which meant you were adding probabilities. So let's do this problem again, but this time we're not going to list our sample space. We're just going to use this formula. So the probability of the die greater than 3 and the coin landing on heads. So that means all we have to do is find the probability of getting greater than 3 and find the probability of landing on heads. So if you just roll a die, what's the probability that it'll be greater than 3? 3 out of 6. Okay, remember you're giving me a fraction, not just the numerator. So the probability of rolling a number greater than 3 is 3 out of 6. And then the probability of landing on heads is 1/2. Okay, so all we have to do is just get these individual probabilities. Notice that 3/6 reduces to 1/2. And so I just have to multiply it together, and 1/2 times 1/2 is 1/4. So we got the same answer no matter how we worked it out. This way is shorter. using the formula than having to list the list of 1 heads, 1 tails, 2 heads, 2 tails, 3 heads, 3 tails, and so on. Okay, because assuming that the problem's not going to give you that list, you'd have to recreate it yourself. So using the formula would be a lot faster. If the probability that South Florida will be hit by a hurricane in any single year is 5/19, what is the probability that South Florida will be hit by a hurricane in 4 consecutive years? Now, that would just be in 1 year. So we're looking at 4 consecutive years. So this is an and problem without using the word and. Okay, because think about what 4 consecutive years means. It means in the first year, and in the second year, and in the third year, and in the fourth year. Okay? So if you have a problem that says consecutive times, or so many times in a row, or something like that, then that is the same as an and problem. So therefore, we're looking for the probability of a hurricane, and a hurricane, and a hurricane, and a hurricane, 4 years in a row. Well, what are we supposed to do with the probabilities when we have an and? Multiply. So we're really looking at find the probability of that hurricane in 1 year times the probability of that hurricane in 1 year times the probability of the hurricane in 1 year, and so on. So the interesting thing about this textbook is I started using it when we got hit by 2 hurricanes in 1 year. And coincidentally, this book had this problem in it. So everybody said, oh, that's a high probability because we got hit 2 years in a row, 2 in 1 year, and so on. Okay, so we're going to take 5/19 and multiply it times itself 4 times. That's basically what you're doing. 5/19 times 5/19 times 5/19 times 5/19. Now, there's another way you can look at this. When you multiply it the same number times itself so many times, what are you really doing? Yeah, raising it to the 4th power, or whatever, however many times you're multiplying it. Okay, so the shortcut, if you need to list this answer as a fraction, then I would do numerator and multiply it, and then denominator and multiply it. So you could do 5 to the 4th, and that'll give you your numerator, and 19 to the 4th will give you your denominator. If you need to list this answer as a decimal, well, then you can put the entire 5/19 into your calculator, especially if you have parentheses, and raise it to the 4th, because then your calculator will give it to you as a decimal. So just keep that in mind, what they're asking for is the answer, what will make it easier to solve it. Okay, so I have the answer written 2 ways here. So as a fraction, we get 625 over 130,321. And as a decimal, it's 0.0047. That's a really small chance that South Florida will get hit by a hurricane 4 years in a row. So again, it looked like it was getting pretty high, but we got hit, 2 years in a row, and then I think the next year South Florida didn't get a hurricane. It came close, but it didn't actually hit South Florida. This one is the one that has the mistake in rounding. It should be 0.0048. What is the probability that South Florida will not be hit by a hurricane in the next 4 years? Okay, what other keyword do you see here? Not. Okay, so we're really looking at the probability of no hurricane. In 1 year, we have to figure that out first. Okay, so the probability of no hurricane in 1 year is 1 minus 5 over 19, which is 14 over 19. So now that we know that, now we can see what the probability of no hurricane and no hurricane and no hurricane and no hurricane gives us. Okay, so taking that 14 over 19 and multiplying it times itself 4 times. Okay, so as a fraction, we get 38,416 over 130,321. And as a decimal, that is rounded correctly, 0.2948. So notice that the probability that South Florida would get hit by a hurricane in 4 consecutive years was only 0.0048. That means that's less than 0.5% that we would get hit by a hurricane in 4 consecutive years. Now, the probability that we would have no hurricane in a single year, in 4 years, meaning no hurricane the first year, no hurricane the second year, none the third, and none the fourth, is 0.2948, which is about 30% chance. So notice that it's much more likely that we would have none in 4 consecutive years than it is that we would have one every single year for 4 years. Now, 30% still is not a high probability. It's still below that 50% range, right? Okay, so then the real question would be, what is the probability that South Florida will be hit by a hurricane at least once in the next 4 years? And that's what a lot of people ask themselves after we got hit by hurricanes so many times in those 2 years. A lot of people moved away because they're like, I don't want to deal with these hurricanes anymore. All right, but really you want to know what's the chance that you'll get at least one in 4 years, and can you live with one in 4 years? Okay. All right, so for this one, you're looking at the keywords at least once. Okay, at least once. That's what you're looking at for this type of problem. And this one's a little bit more complex than the last two. You have seen the words at least once in a previous chapter. Yeah, it was chapter 3. What did we study in chapter 3? Truth tables, okay, logic in general. So chapter 3 was about logic. And you saw the at least once in the word some. Okay, so when we talked about quantified statements in the word some, that was the same as at least once. All right, so the reason I'm bringing it back to that is we know that the probability of something not happening is 1 minus the probability of it happening. Okay, so if you guys remember negations, the negation of some are was none are. Okay, so it went from some to none, if you remember that. Well, negations are sort of like opposites. Okay, the opposite of at least one is really none. So the probability of no hurricane in 4 years is the same as 1 minus the probability of at least one hurricane in 4 years because those are opposites of each other. It's either not going to happen at all or it's going to happen at least once. Okay, those are opposite events. And so that's how this formula actually helps us to figure it out. Okay, so if you rearrange this formula, you get the probability of at least one hurricane in 4 years equals 1 minus the probability of no hurricane in 4 years. Now, I skipped all the work of rearranging it, but that's just algebra, right? You can move this one, add it to both sides, and then you can subtract this one to both sides to get it over to the other side. So all I did was I rearranged it using algebra, and here's what your formula is. So the probability of something happening at least once is 1 minus the probability that it doesn't happen at all. Okay, well, we already know what the probability of it not happening. That's what we just figured out. It was 0.29 something, right? Okay, so all we have to do is say 1 minus 0.2947. Oh, and this is where it wasn't corrected, right? Wasn't it 0.2948? Yeah, okay. Yeah, so it's rounded wrong on this screen. It was, the other one was fine, but this one was wrong. So it should be 0.2948, which equals 0.7052. I think that's right. Yeah, so this final answer was corrected. Okay, so sorry, it was somebody else who came up with this problem, and I tried to fix it. I just did not fix it successfully. Okay, so it should be 1 minus 0.2948, which equals 0.7052. So the probability that we would get hit at least once in 4 years is about 70% chance. Those of us that have lived in South Florida for a while, we know, yeah, it's a pretty high probability that we're going to get hit by a hurricane. And you know what? We're okay with that. We've lived through them before, and we'll live through them again. Okay? So that's pretty much the attitude of South Florida for, stereotype there. Okay, now it was just that this was written wrong on the slide. Okay, so it would come out to exactly that answer there. All right, so on your handout, I know I didn't make it really clear on the handout, but on the bottom of the handout there's this little thin box, and it's really for this formula right here. So the probability of an event happening at least once is 1 minus the probability the event doesn't happen. So if you see the keywords at least once, then you're always going to do 1 minus the probability that it doesn't happen at all. So you actually have to find that answer first. That was our second question. You have to find that answer first and then substitute it into this to find your actual answer for at least once. Now, obviously, the time periods have to match. If it's in 4 years, then the other one has to be in 4 years. If it's in 3 years, then they both have to be in 3 years as far as what you're looking for. Okay, 2 events are dependent events if the occurrence of one of them has an effect on the probability of the other. All right, so this is the difference between independent and dependent. So for example, you draw one card, and then you go to draw another card, but you still have the other card in your hand. So if you draw a card and you're keeping it before you draw the second card, what's happened to the deck? It's one less card in that deck. So you have changed what's about to happen. Okay, those are dependent events. Now, if you draw a card and you replace it and you put it back, then those are independent events because you have put that card back and everything's back to normal. So make sure you're listening to keywords like that. Now, if they are dependent events, if the first event affects the second one, then you're still going to be multiplying your probabilities. You've got a probability of A and B, but here's the difference. And I don't really like the word given in there. I keep forgetting to change that in the PowerPoint. It's the probability of A, and then multiply it times the probability of B, assuming that A has occurred. Okay? Change that word given to assuming. I like that word better. So the probability of A times the probability of B, assuming that A has occurred. Okay, so you're dealt 2 cards from a standard 52-card deck. Find the probability of getting 2 aces. Okay, so here's what you're hoping for, 2 aces. Now again, you're dealt 2 cards, so when you get the first one, that's not going back into the deck. You're going to keep it, and then you're going to get the second one. So that's how these are dependent events. All right, so we are finding the probability of an ace times the probability of an ace, and again, change this word to assuming that ace was dealt first. Okay, so when you get the first card, what's the probability of getting an ace that first time? Say that again? 4 out of 52. Okay, there are 4 aces in the deck out of 52 cards. Okay, so there's your first probability. All right, so now you got your first card, and you need to assume that that's an ace. So now what's the probability of getting another ace? 3 out of 51. Good, because not only have the number of aces gone down in the deck, but also the total number of cards have gone down as well. Okay, so 3 out of 51. So this is how that changes. You need to think about what's happened before you write down your next number. Now, you're still multiplying here, so it doesn't really matter if you reduce your fractions. You can if you want. You can also notice that stuff cancels, diagonally and all of that stuff. Okay, now I did go ahead and reduce my fractions next. So 1 over 13 times 1 over 17, which then gives me a final answer of 1 over 221. But it does not matter if you reduce first or if you reduce after you have multiplied. It's up to you. Typically, it's easier to reduce first because then your numbers are smaller. Okay, so any questions on this and? This is another and problem. Notice that the word and was not in there, but it is an and problem because it says find the probability of getting 2 aces. In other words, find a probability of getting an ace the first time and an ace the second time. Okay, so make sure you're keeping track of what an and problem could look like, meaning that you're going to multiply your probabilities together. All right, conditional probability. So you're looking for the conditional probability of B given A. This is why I don't like that word given in the previous problems. The textbook used the word given too many times, I think, and it could confuse you. So you write it like this with this vertical line. So the probability of B given A, the vertical line means the word given, is the probability that event B occurs computed on the assumption that event A occurs. So in other words, it's like getting a hint. It's like, okay, me telling you, you know, I have 6 numbers in a hat, and I pulled out a number and I said, okay, so it's numbers 1 through 6. And I pull out a number and I don't show you and I say, I give you a hint, it's an even number. And you now know some more information about what could be, you know, what could have happened. So that's conditional probability. It's only one event occurring, just one thing's happening, but you're given some more information about what it might be. All right? So, for example, let me give you the formula first, sorry. So the formula of the probability of B given A, now, the book gave it to you in set theory first here. Notice that this is from chapter 2. The cardinal number of B intersect A, which is the same as saying the number of outcomes in common to B and A. So how many times can you get both, in other words? Okay, so what the number of outcomes in common to B and A. And then the denominator is the cardinal number of A, or the number of outcomes in A. Notice that the denominator is the same as the second thing listed in your parentheses, if that helps you to remember. It's always your given information, your hint, in other words. So the numerator is what they both have in common. The denominator is only the given part, the second part. You are dealt 1 card from a 52-card deck. Find the probability that you will be dealt a heart, given that the card is red. All right, so in other words, I'm looking at the card before I give it to you, and I said, I'll give you a hint, it's red, and so you have more information about that one card. All right, so you're looking for the probability of a heart given that it's red, which means you want the number of hearts that are red. What do they have in common? Hearts and red, those two things, over the number of red cards. So the denominator is always just the given part, given that it's red, so you need the number of red cards. All right, how many hearts are red? How many hearts are red? 13. There are 13 hearts and they are all red. Okay, so 13 is your numerator. How many of the cards are red? 26. Half the deck is red. So filling in your numbers, you get 13 over 26, which reduces to 1/2. Now notice the difference if you didn't know that that was red. The probability of getting a heart in general is 1/4. Okay, the 13 out of 52, 1/4. But once you know that it's a red card, that probability goes up. And now the probability is 1/2 of getting that heart because you know that it's also red. Okay, what's the probability of a heart given that the card is black? 0 is correct, because notice your numerator would be the number of hearts that are black. Well, none of your hearts are black. That's impossible. And so it's 0 out of 26, but it doesn't really matter. It's 0. It's impossible to get a heart now, given that the information is black.